Here's just an illustration of the folded sheet concept. You can see that the folded sheets act both as longitudinal beams and transverse beams. Again, it's using the strength of that material along two directions. Because it's an isotropic material like reinforced concrete, we can stress it in multiple directions and use its full strength for the structure. This represents an experiment we won't recreate here in the class, but it's something you could do on your own, where by separating the extreme fibers of the paper by using a folded sheet, you can see that you can develop a robust slab type structure. This is a slightly more complex folded sheet arrangement, but the principle is the same, that you're separating the extreme fibers of the material to create this kind of complex and rigid shape. This would be analogous to perhaps some of the complex curves that are formed in the body of a unibody car. It gets its strength from its geometry. Here you see a rotational hyperboloid, and you're probably not going to see this real commonly in building construction, but it's another example of a complex shape where we have these compound curves. The one application where you'll see something similar to this is a cooling tower associated with a power plant. And in this cooling tower, they're essentially pumping water to the top and allowing it to cascade to the bottom, and in the process evaporate. And those towers develop a convection current of air coming through, and it turns out that this hyperboloid shape is useful in assisting that airflow. Again, not real common to building construction, but it does illustrate the use of complex curves to generate a surface. These diagrams just, again, kind of demonstrate this concept of complex curvature in a roof structure, in this case, taking full advantage of the strength of the materials. Figure 11.26 shows a high-par roof, and high-par is a contraction of the mathematical term hyperbolic paraboloid, which is just really kind of the type of shape that's used to construct this. This type of structure is typically made out of reinforced concrete, and its load is borne on these points out here on these columns. Now, that means that there is this kind of curved shape that this thing takes on between the columns, and just like any other arch, this curve wants to flatten out and produce an outward thrust on these columns that are supporting. So these columns have to be robust to that type of load. The other thing is that when the weight is placed out near these other kind of apexes of this, tension develops along this top chord of this concrete casting here. And so that's typically handled either post-tension with tendons, or could be handled with reinforcing bar. But once those concerns are taken care of, this is a very strong roof. In fact, there's some calculations that show that when this is uniformly loaded, say for instance with snow, that no one part of this roof is more tensed or more compressed than any other part. In other words, it is kind of uniformly strong throughout its area. There is no weak link in this roof. The result of that is, again, a very, very thin roof structure for the span that it covers, which means lightweight, which means less structure underneath. And again, it's just a very efficient way to use concrete, reinforced concrete. In this section of the text, the authors discuss groined vaults. And essentially what a groined vault is a non-developable intersection of two arches. And you can think about if you were to load, for instance, this arch in compression, if you were to load it with weight from above, it's going to develop outward thrust. It's going to want to push the ends of the arches out. That, however, is resisted by the base of the intersecting arch, so that this is inherently stable, and the only way to collapse this is basically to have a compression or tensile failure in the materials of the arch. So you don't see this real frequently in modern commercial construction, but in the days when our knowledge of building materials were very limited, this was common in typically in cathedrals and construction of that type, where they had to span great distances with very limited materials. Again, different applications of the hyperbolic paraboloid roof. You can see that it's a roof that looks planar, but actually all of these are complex curves. And that characteristic of being complex makes them non-developable, and as such, we are able to gain strength from that. Again, some more complex high-power roof structures. So this is an awning at an airport, at Newark Airport. Material of reinforced concrete. The complex shape gives it its strength. Very, very thin for the distance that it spans. Now, here's a structure with complex exterior skin, and this is really more just an illustration of an architectural principle. If you think about this type of building, it's entirely glass on the exterior. So this is a steel skeleton curtain wall type building. The structure itself is the steel skeleton inside. The glass is simply there to create a separation from indoors and outdoors. So while it's not structural, it illustrates how sometimes architects will use this type of shape in the development of a certain aesthetic that they're pursuing. Complex shapes go beyond roof structures, and here's an example from civil engineering. The dam on the left is a typical gravity dam. This is the garden variety dam. You can go all over Wisconsin and see this type of thing. And essentially the way this thing works is it's just sufficiently heavy that an adequate amount of friction is developed with the soil to keep this dam from sliding with the weight of the water. Well, this is effective if you've got to span a narrow gap. But suppose you've got to span something large, like Lake Mead, and you need to hold back a large amount of water. The amount of force that you're going to be able to develop, this hydraulic pressure is going to be able to develop. And I guess, if I'm going to diagram this accurately, I should show that these lines are longest at their bases, because that's where the static pressure of the water is the greatest. But regardless, if you're going to span that kind of distance and that kind of height, you're going to need a structure that's so massive, that uses so much concrete to do it by gravity alone, that it'd be cost prohibitive. So here's an alternative approach. It's a thin shell dam, and if you were to look at this, for instance, if you were to look at the Hoover Dam from above, you'd see that its shape is actually an arch with anchorages on the end. And the idea here is that as the thrust of the water loads the arch, the water thrust is nice because it's totally uniform from left to right, and it increases predictably with changes in depth. That's going to try to push this arch out of here, but because it's anchored, it's going to develop an outward thrust. So we still need gravity, we still need massive stuff to resist this thrust, but in the case of the Hoover Dam, it's the walls of the canyon. So you're using something that's cheap. You're using existing earth kind of as the abutments to the arch. So when you get to large spans, when the dams need to do something complex, then you tend to see these thin shells as opposed to the more garden variety gravity dam. The remainder of the chapter talks about thin shell techniques for construction of domes and similar type structures. And here you see a Binney shell, which was named after its inventor. Basically the way this is constructed is a balloon that has this approximate shape, is inflated and then covered with wire mesh. And the wire mesh serves as the reinforcement to the concrete. And then concrete is sprayed onto the exterior of the balloon. A product that's commonly used in the construction industry is called shotcrete, and it's basically concrete that's sprayed out of the end of a gun and will stick to the outside of this structure. You may see shotcrete used, for instance, downtown on the isthmus when they excavate foundations. You have to have something to keep the soil from sloughing into the excavated hole, because typically the walls of the excavation need to be near vertical. They don't have the luxury of cutting the walls of the excavation back beyond the friction angle of the soil. So there'd be a number of ways you could retain that. You could drive sheet piling, for instance. You could drive piles and drop in breastboards and rakers. That's all expensive. So an alternative method is you spray shotcrete on it. Another place you may see shotcrete used is if you have a historic masonry building that's starting to fail. So historic masonry buildings had lime mortar, which is water soluble, and that means that if the building's not been maintained over the years, the outside of this building, the exterior load-bearing walls, are going to be in a state of disrepair. The one that comes to mind for me is the tavern In Mount Vernon, Wisconsin, the Gone Fish Inn is an old masonry building, and the parapet wall on that had started to fall off. And so the repair that the property owner made there is they had shotcrete sprayed on the outside of it to kind of encase all of the bricks that were at risk of falling out on the patrons of the tavern. So similar process here. The upshot is that the formwork is basically just the balloon. So the balloon is inflated, the concrete sprayed on the exterior of it, it's given sufficient time to harden, and then the balloon is deflated. And the balloon gets packed up and it gets taken to the next job site. So there are really very little overhead cost in this operation. Once the balloon's constructed, they can make these things rapidly and for not very much money. The other thing is, because the material is used so efficiently, these shells can be extremely thin for the spans that they create. So it's an impressive construction technique that we don't see a ton of, but a good way to cover a large area. Again, just a simple complex curve used in a thin shell arrangement for a staircase that is surprisingly strong for the amount of material in it. Here's an illustration of groined vaults, and you can see that these were stacked out of corbelled bricks. And we've talked about corbelling earlier in the course. This idea with corbelling is that you can stack bricks in such a way that you don't need any false work to create the arch. So the upshot of this is, under kind of traditional methods, you could only construct this with a wood false work. You'd have to build the structure out of wood, cover it with a brick, and then somehow remove the wood, which was holding up much of the weight of the brick. And a traditional approach to that would be to burn the wood formwork out of the way. With this corbelling technique, the entire structure could be created without false work, and that substantially reduced the cost of construction. And remember, the name of the game in construction is making money. Finally, this is the last thing discussed in the chapter. This is a method from the former Soviet Union, and again, it's a corbelling method. So some simple beams are cast out of reinforced concrete and hoisted into place, and then by corbelling these tiles, they're able to stack this dome without any false work. So again, another pretty efficient way to get a strong structure, long span, and minimal construction costs. Hopefully this has been insightful in terms of some of the things that I hoped you got out of the reading. As always, if you have any questions, feel free to get in touch with me.